Hello everyone, I'm Andrea Cozzumbo. I'm a third-year PhD student at GSSI, Grand Sasso Science Institute, and it's a pleasure to be here and talk about my work that is about model independent constraint with gravitational waves and in particular with standard sirens. So this work is available at this QR code, and it is done in collaboration with this bright scientists. And I want to frame this in the context of dynamical dark energy. Also, even if we started this project before the data release 1 of DAISY, and you see here what you saw a lot today, and a beautiful presentation from Eric describing this parameterized equation of state of dark energy that embodies all the Thawing and freezing models for equation of state of dark energy. But for us, in the context of this work, there are just two parameters. And as you know, in this W0, W8 plane, you have at least a 2.5 sigma from the first data release of DAISY of discrepancy from lambda CDM. And I just want to put it in the framework of what we did, that is analyzing this FDE function, so the evolution of dark energy as a function of Z. You just need to plug this parameterization in the equation, in the expansion history, and you get this FDE of Z, and you see it in black, in solid black here. But then you can also perform like a model-independent approaches, like the one that you see here in blue, that is from the data release 2 of the DAISY collaboration. So I spoiled a bit this slide, but the idea is, why should we need gravitational waves? In my opinion, they provide a new probe, and this is great because they provide orthogonal information from what we have today, from BAO and supernovae. And a more practical reason is because they provide a self-calibrated measure of distance, because you can infer the luminosity distance directly from the polarization of the wave. So in all the astrophysics of gravitational wave, you need to do cosmology, the luminosity distance, and a tracer of the redshift of the event to constrain H of Z. And the redshift in this case, so there are many ways to do it. And in the context of this work, we use bright sirens. Bright sirens are depicted like this in a funny way. So you have your galaxy and you have your binary neutron star merger. So you have the coalescence, and then the merger can produce a gamma-ray burst, so an electromagnetic counterpart to the gravitational wave counterpart. And so on Earth, you have these two guys that are Fermi and Swift, that are high-energy satellites. And you get the GRB information, and then with follow-up from ground, you get to pinpoint the host galaxy of this event. But then we need also the gravitational wave to do multi-messenger cosmology. Today I'll talk about future interferometers and the capabilities of future interferometers. As you see here, I put like a representation of what is Einstein Telescope, the futuristic European observatory for gravitational waves. So the schematic is that we get the Z from the host galaxy association, then we get the luminosity distance from a Fisher matrix approach with a code that we developed at GSSI that tell us what is the error on the estimation of the luminosity distance that we can get from different networks of third generation or also second generation interferometers. And then we get the HZ information. And in this case, I'll talk about GP, so Gaussian processes in this model-independent approaches a bit later. And I just want to set the ground, telling you that we used really observed GRB events to construct our dataset. So we took all this data from Fermi and Swift, so 20 years of data, and then we selected what we consider the one that most probably are merger-driven, because as I told you, we need both the gravitational wave and the electromagnetic counterpart. So the electromagnetic counterpart was seen in these events, and the idea is what is the insight on cosmology in the case we would have had Einstein Telescope operative during the data taking of this of Fermi and Swift. And here you see the dataset represented as a function of z, and this is the probability of chance coincidence, meaning is the probability of wrongly associating the host galaxy, the event to the host galaxy. And so the results that I will show you, are taken with only 38 events that are these golden sample events. And also the redshift estimation is very precise. The other bit of information that you need is gravitational wave posterior. So we have developed this code, GWFish, that basically gets you the luminosity distance posterior, taking into account all the degeneracies that you can have with other parameters of the gravitational wave inference. So like the chirp mass and the mass ratio, and also the inclination angle, as you see here. Then we improved it. We implemented physical priors, and then we also, in this case, in this work I present, we included also correction for peculiar velocities. And finally, you need a bit of information for non-parametric approaches, so what I call model-independent approaches. But you already heard about this. So we use Gaussian processes to, instead of parameterizing this FTE, as I showed in the second slide, with two parameters, you get that FTE is a function in the space of function distributed as a Gaussian process. So cumulatively, all this function behaves as a with a Gaussian distribution that has a mean around this FTE equal to 1, that is the behavior of lambda CDM, and then is as a kernel that is parameterized with these two hyperparameters, sigma f, that is the scattering around the mean, and LF, that is the how smooth is the function, is the correlation length of the function you are drawing from this space. So the strategy is to generate two mock catalogs, so of GRB events. One where we include, so we generate our universe accordingly to lambda CDM Planck 18, and one with a dynamical dark energy. In this case, we use a phenomenologically emergent dark energy that is the best fit of this data set here. And why we choose this? Because we want to be very careful, and we know that these models should fit the data and should not be totally different from lambda CDM phenomenologically. And then we feed the data with the parametric and non-parametric approach, and we compare the results. So here I'll show you the results with an injected lambda CDM and a reconstruction with lambda CDM. So as you see, we get the cosmology inside the 1 sigma, but here I want to show you how different interferometers can give you different constraining power. So LVK, in the most futuristic, LVK stands for LIGO Virgo Kagra, so the second generation of interferometers that are running right now, but this is the more futuristic configuration that we will have. Won't give you any information basically on the matter abundance, and this is why we include also the Phantom Plus data, so supernova data that basically they are uncalibrated. So what you're doing in the pink contours is to calibrate a supernova with gravitational waves. And so you see that you get more information out of it. But I want to show you that Einstein Telescope alone, due to the fact that third generation interferometers will have a bigger horizon and will test h of z instead of the linear expansion in the local universe, will be able to give you out of the box the very nice contours, and with Phantom Plus even more constraining. What if we fit the data with a CPL model or W0WA, so with a dynamical dark energy? The idea is that you have a bigger parameter space, so you get bigger contours. But what and here you see the comparison with the lambda CDM case. This is all done with just 38 events of GW-GRB multi-messenger events. And what you have to compare with actually is the capability of a parametric and a non-parametric approach. And this is what we do here. So we generate our universe with a PED, phenomenologically emergent dark energy model. That means that at a certain point, this the abundance of dark energy emerges and then take the expansion history of the universe. And what you see here is the contour that are given by CPL, so parametric approaches, and GP, that are non-parametric or model-independent approaches. And generally, we get a factor 1.5 more constraining power from model-independent approaches with respect to parametric approaches. But the other thing that you could notice is that if you fit lambda CDM that is rigid in the evolution of the dark energy behavior, you get biased results. So using model-independent approaches is fundamental also not to get bias from your model. Here, with model-independent approaches, you can also do the reconstruction of the FD. And so, as you see here, this is the lambda CDM behavior, the dashed black line. Then you have the injected cosmology in solid red. And you see that the Einstein Telescope alone is not able to distinguish, not even, so the lambda CDM behavior is within the 1 sigma region, but also DAISY year 5 data are not able to distinguish the real injected cosmology, while the combination of the two, so a multi-probe approach, can do it. I don't know if you can see it, but at least in this region of the of Z, you can get more than 2 sigma discrepancy from the lambda CDM behavior. So this said, I just want to tell you that this approach can be generalized to do the same thing that we did with this function in the context of dynamical dark energy with a modified gravity theory. So the idea is that somehow they are correlated, as Eric was saying before, one can source the other, so a modified gravity theory can be seen as a dynamical dark energy. And in the gravitational wave community, there are plenty of papers that give us the generalization of the propagation equation of gravitational waves with a modified gravity theory, and then you can massage a bit the equation and get that you the new luminosity distance that this modified propagation of gravitational waves follows is proportional to the electromagnetic one, so the one that photons follow, with a function that is dependent on Z. And actually, what is typically done is to parameterize it with these two parameters, C naught and N. But the same thing that we did with dynamical dark energy, we could do with this function, that is a function of Z. and to trace in a model-independent fashion this ratio. These are preliminary results, and the idea is that within just using gravitational waves, you get a good constraining capabilities, because different papers claim to do it with something like thousands of GRB gravitational wave multi-messenger events that are crazy numbers. Here we are doing it with just 38 events. And then obviously you can add information, and for example from Pantheon Plus, or also the distance information from CMB in the green contour here, Planck 18, and you get better and better constraining power. In the same way, you can do the non-parametric reconstruction of the ratio between the DL of modified gravity and DL of GR, or DL GW over DL electromagnetic. And as you can see, you get consistent results. Here we were just injecting the GR behavior, so you get the GR behavior again. So here I leave my conclusion. I want to stress two things. The first is that all this work was done in the context of so within the use of the most advanced tools that we have, CLASS, Cobaya, and MontePython in cosmology, and our likelihood will be available for you to reproduce our data, our results, and also to try to see if you can get different things with different probes, with different multi-messenger probes. And the other thing is that with just less than 40 GRB events with the gravitational wave counterpart, that is a reasonable number for Einstein Telescope, the Einstein Telescope epoch, we will have this constraining power on the dark energy density, dark energy evolution, and the nature of gravity. But we need instruments that are able to catch both the gravitational wave and the electromagnetic counterpart, and this is crucial to have these such numbers and have this orthogonal way to probe cosmology. Thank you.
Thanks, Andrea, for a very nice talk. So, questions, please?
Thank you for your interesting talks. I have one question and one comment. So the comment is, you are showing that currently there is no information that you can get from this sample of 38 gamma-ray bursts, because it's pretty uninformative. So what it is the foreseen in the future? So if you have computed how many years and how many more GRBs you need to reach the same precision that, for example, has Pantheon or Pantheon Plus on omega m parameters I was showing yesterday in my talk for the GRB fundamental plane.
So the information from you were talking about the capability of GRBs or the gravitational waves to constrain cosmology?
So the capability of GRBs, currently you have 38 in your sample,
yep.
And this is showing from your contour plot, they're not informative. So how many more do you need? So
somehow, so here you see that I jumped on this sample, but actually we have 61 events that are inside this set, and they are not golden samples because we don't really trust the association to the host galaxy, so the reconstruction of Z. So the improvement from this sample to the silver sample, let's say, so this, I think they are 58, no, just a bit more, 50-ish events, is drastic. So there's a big constraining, much bigger constraining power. Why? Because you have these three events at IZ. So you are going to test at higher Z the evolution of dark energy, and so you get better constraining power. So the idea is that if you get probes like Theseus, so for GRB in the very high redshift, for sure you will have more constraining power.
Yeah, but for Theseus, if it is approved, we have to wait until 2037 until it's launched.
Yeah, sure. For sure, this is in the context of Einstein Telescope. So the Einstein Telescope has at least 10 years of construction.
Okay, and the other comment is that you mentioned that you checked several catalogs. Did you check also the largest GRB optical catalog that we published last year for optical observation? You can check the ENOT et al. 2024. We have 64,000 data points in optical, so maybe you may find additional constraining power adding more data to your sample.
Here, I'm sorry I didn't cite my my source, that is Fong 2022. So the catalog of Professor Fong is huge. So it doesn't. So usually you have binary neutron star merger that are associated to short gamma ray bursts. But actually, we are also using gamma ray bursts that are supernova-less, so the ones with kilonova that most probably are associated with a binary neutron star merger. So we have the gravitational wave counterpart. So I don't know about the catalog that you're citing.
It has 64,000 data points, 530 GRBs, and it is 570 instruments. So you may check it out.
For sure, we can check, and it's great to have more and more data. So,
any other questions? Eric?
Very nice talk, Andrea. Can you give us some intuition as to when you allow more freedom through the GP, you're still getting more constraining power as well?
More than with respect to the parametric approach?
That's right. So you're allowing more freedom, and yet somehow your constraints are smaller as well. How should we think about that?
So my intuition is that so in the case of Gaussian processes, you have two more degrees of freedom that are hyperparameters. They are not associated to physical parameters like W not WA. But yes, so I think you have more freedom in the choose of the behavior of dark energy. So you can fit more easily your data points, and I think that the constraining power, the additional constraining power, is coming from that.
And thanks to Andrea.